Okay, so here we are with Unit 8, Lesson 5, and it's kind of a continuation of Lesson 4. We're going to get into endo and exothermic potential energy diagrams, and as I had said before, you need to be able to take just a look at this equation, this diagram, and just tell from looking at it whether it's endo or exothermic. And the way to look at it is this: if you look at the the y-axis, remember we don't really pay attention to the x. The y-axis is energy in kilojoules, and you can see that the reactants have this much potential energy. The products have this much. So you can see the products, or what you end up with, has a lot more energy than what you started with, which means you gained energy. So this represents an endothermic potential energy diagram. In addition to that, you need to be able to label all 6 of these parts of any potential energy diagram, either one for endothermic or exothermic. So what I'm going to do is, just to go through this, I'm just going to make up a scale for the y-axis, just so that we can look at the numbers. You don't really need to do this all the time, but I'm just going to do this. I'm going to make this, let's see, I'm going to make this 50 kilojoules, and then I'm going to make this 100, and this will be 150, this will be 200. So the thing to do with all of these is you notice how they put a dashed line next to the reactants. You should do that with the products also, and then they did a top one here, and that will make it a lot easier. So what you're looking at is how much potential energy the reactants have. So the potential energy of the reactants is this section here. That would be section A. That would be about 50 kilojoules. Here's the products. So the products would have this much potential energy. That would be B, and that would be about 150 kilojoules of energy. Potential energy activated complex. The activated complex is always the entire height of the diagram. It's always going to be the largest number. That's 200 kilojoules of energy. All right, and now you're looking at what's called the activation energy, and notice they have it twice. It's not a mistake, because it's actually 2 different things. It's the activation energy for the forward and the reverse reaction. So the forward reaction is the reaction that's moving from left to right in this direction. The reverse reaction would be if we are looking at this reaction but reading it from right to left, and we'll go over each one. So the activation energy is, if you're standing here, here's you sitting here, standing here, and you want to get up to the other side, you have to climb up this hill. Well, the height of this hill from here to here would be the activation energy. That's the amount of energy in kilojoules you would need to start the reaction. That would be D for the forward reaction. That would be from 50 to 200, so the forward reaction would be 150. Now, if you're reading it in the other direction, because remember we said that the reactants react, they form the products, but the products can then react and reform the original reactants. That's the reverse reaction. So now we want to read it in this direction. That's the reverse reaction. And again, still you consider, what hill do I have to climb to get to the other side? Well, I have to go over a much smaller hill. It's only from here to here, and that would be E, and that's only going to be 50 kilojoules. Now we want to look at delta H. Delta H is the heat of the products minus the heat of reactants. Heat of the products is 150 minus the heat of the reactants, which is 50. So delta H is 100 kilojoules. And that would be represented by this section here. That would be F, delta H. And it would be a positive because it's an endothermic reaction. And that is the endothermic reaction. Let's take a look at the exothermic one. And I'm going to cover this, do the same thing. I'm going to go through, but I'm going to go through it more quickly this time. We're going to make, again, we'll do this, we'll make this, let's do this as 25, just so the numbers are different. Halfway in between will be 50. That means this will be 75. And this will be 100. Just making these numbers up, but you can do that. So the potential energy of the reactants is this. That's going to be A. That is 75 kilojoules. Here's the products. That's B. that's going to be only 25 kilojoules. The activated complex is this whole section here. That's going to be the entire height, which in this case is only 100. The forward reaction activation energy is the hill that you have to climb, which is only this hill right here. So this is going to be, this is D. This is only going to be 25. This is the hill you have to climb for the reverse reaction. That's E. That is going to be from 25 to 100, that's 75. And delta H is the heat of the products, which in this case is 25, minus the heat of the reactants, which is 75. You notice you're going to get a negative value. So delta H is negative 50 kilojoules. That would be this here. That is F, is this section here. It's negative because it is exothermic. Now the other thing we want to look at is, and this is what they ask you about, if I added a catalyst to this, how would it change the reaction? Well, a catalyst only changes activation energy and this. So a catalyst affects C, D, and E. It does not affect the heat of reaction. It doesn't affect the potential energy of the reactants or the products. So what would it look like? Well, if I added a catalyst to this, here's what would happen. I'm going to make it, let's make it a different color so you can see the difference. Let's make it blue. The reaction would start out exactly the same, but what would happen is it would not go up as high, but it would end and begin at the same exact place. So this line is with a catalyst. They have actually asked you to take a diagram and draw in what the line would look like, or what the graph would look like with the catalyst. And this stands for W/O is without catalyst. And make sure that you copy this down. This is extremely important. And that is it for this lesson.